Alright, so now we know how to solve second order differential equations with constant coefficients when the corresponding characteristic equation has different real roots and different complex roots. In other words, we know what to do whenever the discriminant b squared minus 4ac is non-zero. So now we are going to figure out how to solve this if the discriminant is 0. Well, here is an example of such situation. But before I go on, let me ask you a few questions that are useful for your for understanding. If I conducted an actual lecture in class, I would pause the lecture and ask the audience. But now, since you are watching me, it means that please, you should pause the lecture still, try to answer these questions for yourselves, and then compare with my answer. Alright, how can we interpret the equation b squared minus 4ac algebraically? Well, the answer is that in this case, if we write down the corresponding quadratic polynomial ax squared plus bx plus c, then b squared minus 4ac equals 0 whenever this is a complete square. So this is a linear function squared. So that's the algebraic interpretation. Geometric interpretation is, it means that if we plot the parabola ax squared plus bx plus c in the plane where the one of the axes is x and the other is whatever, then this parabola is going to be tangent to the x-axis. That's the geometric interpretation. And then in terms of calculus, if we introduce the function f of x, ax squared plus bx plus c, then in terms of calculus, this function is going to have a common root with its own derivative. So then there is a certain root such that f of r equals f prime of r equals 0. So these are the two interpretations of the fact that b squared minus 4ac equals 0. Alright, now suppose that this actually happened, right? So it means that we have a repeated root, r is a repeated root, and this whole thing a r squared plus b r plus c is actually the complete square. So it is going to be, I believe, a times r minus b over 2a plus b over 2a squared. Well, in this case, the function e to the rt is still going to be a solution, but the problem is that there is only one solution, and from the general theory we know that there must be two linearly independent solutions. So the question is, how do we find another one? And the idea here is to look for the answer in the form y equals some unknown function times e to the rt. I mean, although it looks silly, probably because, of course, if this is true, then v of t is just y times e to the minus rt, which is really doesn't seem to be very helpful. But as a matter of fact, it helps a lot, and I'm going to, just for better understanding, I'm going to show how it works on a specific example, but that specific example is generic in the sense that any other example is going to be the same. So here we are able to recover the general theorem from a specific example. Okay? So it's just a random example. So in this case, so notice that the corresponding characteristic equation is going to be r squared minus 10r plus 25 which means that this is a complete square, so we have r minus 5 squared, and it is 0, of course, whenever r equals 5, right? So it means that the function e to the 5t is a solution of the corresponding differential equation. But we are going to try to find another solution in the form y of t equals v of t times e to the 5t. Alright, and the trick here, as you're going to see in a couple of minutes, is that when we substitute it back into the ODE, then we're going to get an equation on v of t, and that equation is going to be very, very simple. Alright, so if y of t is v of t times e to the 5t, then y prime is going to be, I'm not going to write t anymore, it's going to be, by the product rule, it's going to be v prime times e to the 5t plus v times the derivative of e to the 5t is 5 e to the 5t. Right, so this is y prime. So let me do the second derivative. Y double prime is going to be, I have to differentiate y prime again. So the first term, v double prime plus, times e to the 5t plus v prime times the derivative, which is 5 e to the 5t plus v prime e to the, again, 5 times e to the 5t plus v times 25 e to the 5t. And of course we can, strictly speaking, we can combine two copies of v prime. Well, but anyway, so in the end of the day we need to calculate y double prime minus 10y prime and 25y. So let me write these three things again. So y double prime is going to be v double prime times e to the 5t plus 5 times 2. So I will write v prime times 10 e to the 5t, and then plus v times 25 e to the 5t. So then minus 10y prime is going to be v prime times minus 10 e to the 5t and plus 5 e to the 5t, so plus v times minus 50 e to the 5t. Right? 5 times 10 is 50, minus 10 is 50. Okay, and then 25y equals is v times 25 e to the 5t. Alright, now I'm going to erase this. I don't need this anymore. The reason why I wrote it like this is because now we need to find the sum. The left hand side of our differential equation is y double prime. Well, I'm finding this y double prime minus 10y prime plus 25y. In other words, I need to add these three things together, right? So I'm going to combine everything with y double prime, everything with y prime, and everything with v. Well, but then notice that the coefficients at v are going to be 25, minus 50, 25, so here we're going to get 0. And here the coefficients are 10 and minus 10, so we're going to get 0. And here we only have v double prime. So this whole thing is actually v double prime times e to the 5t. And the question is whenever this equals to 0. And of course now we got a very simple differential equation, which is v double prime equals 0, meaning that v of t is has to be, well, when is the second derivative 0? It's only in the case when the original function is a linear function, right? So now we just found that v of t has to be a linear function. c1t plus c2. Alright, so let me notice that we dealt with a specific example here, but why did it so magically cancel each other? So why did everything cancel each other? And the reason is because, you know, for example, here, if we didn't have these very convenient coefficients, minus 10 and 25, but anyway, no matter what we do, if the reason why they cancelled is because this coefficient minus 10 was equal to twice 2 times 5, and this is thanks to the fact that b square minus 4ac is 0. So it's going to happen whenever this is true, because whenever we have a complete square, right, it means that the coefficient at y prime is going to be double the root of the characteristic equation, and it's always going to whenever we combine this into, well, whenever we try to do this trick with multiplication by v of t, here we are always going to get a cancellation. 10 minus 10, I don't know, 20 minus 20, whatever, is always going to be like this. And because of the same reason, here, when we group together all the coefficients at v, we are always going to get a 0. So whenever our original characteristic equation was a complete square. So it is thanks to that fact that we are going to get zeros here and here. So therefore, we constructed a solution. So c1t times e to the 5t plus c2. Right, so this is our, so let me rewrite it. So our v of t is c1t plus c2. So our y of t is v of t times e to the 5t, so which is c1t plus c2 e to the 5t, and which is exactly this. Now notice that we do have two linearly independent solutions. So the two linearly independent solutions are t e to the 5t and e to the 5t. So in other words, in order to construct the second linearly independent solution, well, the second basic vector, so all we need to do is just to multiply by t. And that's the essence of the theorem. Right? So generally speaking, whenever we need to solve a differential equation, second order, linear, homogeneous with constant coefficients, then we need to set up the corresponding characteristic equation, and if it happens to have a repeated root, which happens if b square minus 4ac is 0, then we just find this repeated root, r. In this case it is minus b over 2a, and then we just take the first solution of the ODE, which is e to the RT, and then in order to construct the second one we just multiply it by t. So that's all.